Hi, welcome to today's video. Today we're going to try to understand how heap sort works. We're going to try to understand it visually first, understand how it works on paper, then we're going to try to implement the code from our visual understanding. Starting with some of the prerequisite information, binary trees. Binary trees are a hierarchical representation of data which state that each node by itself only has two nodes. So essentially, if we were to look at this node only has two other nodes and not a third node going over here. That's the only property that the binary tree states. Each node by itself should only have two nodes. Each of these nodes are known as the left child and the right child. The left child and the right child. The node above the left child and the right child is known as the parent node. Each child can have parent nodes. However, the starting of the binary tree is called as the root node. Essentially, if you were to look at this data structure represented as an array, we would fill it up in using some properties, starting with the parent node always lies at, so given an index I, the parent node for that index I is always going to be at I by 2. If this is a value like 3.5, we consider the floor value of 3. The other property that we need to follow is that the left child for a particular index will lie at 2 into I. And the right child for that node is going to lie at 2 into I plus 1. Let's look at filling this array up in a binary tree representation. So essentially, we have our root node, which is 4, which is going to be starting at index 1. Now, essentially, in computer science, we always follow 0, 1, 2, 3, 4, 5. However, just to explain, I'm using 1, 2, 3, 4, 5, 6, 7. So starting at the root node, we have 4. The left child for 4 is 6, which is going to be at 2 into I, which is 2 into 1, at this position to 2. So we fill up 6 over here, and the right child is going to be into 2 into 1 plus 1, which is 3, which fills up 10. Now we're looking at the left child for 6. The left child for 6 should be into 2 into I. So 2 into 2, 4. This is going to be 15. And the right child for 6 should be into 2 into I plus 1, which is 5, which is 16. Now we look at 10. 10 is at the index 3, so the left child for 10 should be into 2 into I, which is 2 into 3, at 6. The left child for 10 is 21, which gets filled in the position 6. And the right child, which should be at 2 into I plus 1, which is the element 25, which gets filled in the position 7. Essentially, this is the representation of a binary tree. With heap sort, we consider a max heap. A max heap is a representation of binary tree which states that the parent node, therefore, the parent node for each node should have a value which is higher than its child node. So essentially, if we were to fill this up with these same values, we would have 25, and then all the values next to this should be lesser than 25. we consider 21 and 16, which can go either way. 21 and 16. Now considering their children, these nodes should be lesser than 21, and these nodes should be lesser than 16. So we fill it up in the same manner. We fill up 15 and 10 and 4 and 6. Now, there's another representation of a heap structure called the min heap. In the min heap structure, all we consider is that we start with the smallest element, and the smallest element is the root node, and everything below should be greater than that element. So considering the root node starts at 4, the children node should be greater than 4. Filling it up this way, 6 and 10, the children node for 6 should be greater than 6. And the children node for 10 should be greater than 10. This is a min heap structure. However, we're going to consider a maximum heap for our heap sort structure. Heap sort functionality is dependent on two operations on max heap, insertion and deletion. Starting with understanding the insertion in a max heap, let's try to understand it through an example. Let's consider an element 50 that needs to be inserted into this max heap. Now essentially, the naive way to do it would be to just insert it over here, since the max heap property states that the root node should be the highest element in the max heap. However, when we consider a representation in memory, which is an array over here, we cannot extend our array towards the left. So we start by extending or inserting our element into the last position and extending our array towards the right side over here. Now at this point, when we insert this 8, the parent node for 8 is going to be I by 2, which is 4, and 15. So we fill up 50 over here. Now essentially at this point, this binary tree is not a max heap. To make sure that we do a max heap structure, once we insert an element, we compare the inserted element with its parent, which is 15, and then we also compare it, and then if the element is lesser, we swap. Because 50 is greater than 15, we swap 50 and 15. 50 goes in this position and 15 takes the other position. Now again, we compare it to its parent node. 50 gets compared to 21. Now essentially, because 15 is greater, they swap places again. And then 50 gets compared with its parent, which is 25. And because 50 is greater, 50 swaps places with 25. Now essentially, at this point, the tree structure started with 50 at the child node or at the leaf node. However, through swapping, it swapped its structures over here and went back up. And that's how insertion in a max heap structure works. Now let's go ahead and look at deletion. Okay, let's try to understand deletion in a max heap. Starting with the first property, or the first rule of deletion in max heap. We always only remove the root node from our max heap. And this is done so that when the root node is deleted, the next highest element can take up that position and thus maintain the heap structure. Essentially, if we were to remove another element, we would have to do more computations to regain our max heap property. Now that we understand that we are only going to remove our root element, let's remove it from the array or in memory and try to visualize what happens in memory. Now we've removed our root element from our memory. Now which element should take its place? Naively, to maintain our heap property, we should move 21. However, as we can see, if we move 21, we have to move every other element one place back, which takes n minus 1 operations if the array that we have is n. Because we delete one element and then every other element needs to be shifted. So the better way to achieve this is by moving the last element into the root node, which is 6. At this point, we have a binary tree where 6 is removed and is at the first place. However, it does not satisfy our heap structure. To help us satisfy our heap structure, we reheap our binary tree. And how we do that is by comparing both the root nodes, children nodes, and we consider the element which is the greater element, and we switch that. So because 21 is greater, we're going to remove 21 from its place and place 6 over here and 21 over here. Now again, for the elements that swapped, we're going to compare the children node, take the higher element, and place it above. 15 gets placed above, 6 gets placed below. At this point, this is a heap structure, or a maximum heap structure again, since every node's parent has a value greater than its children node. The same thing occurs in memory. Once 6 is placed, it considers its children values, which is 16 and 21, and then gets swapped with the higher value, 21 and 6 moves. And then 6 is again compared with its children nodes, which is 15 and 10, and the value which is higher takes up the 6's place. If the value that was inserted was higher, then the element wouldn't be moved. So if we were to imagine that the element over here was 30, which it wouldn't be since it's a max heap structure. However, in a theoretical situation, if this was 30 and we move this over here, and after comparison, if the elements were both lesser than the value that was moved at the root node, we would not make any swaps. And this would happen at every level. Now, essentially, this is where we start our heap sort structure. Now, essentially, because we've deleted an element, our heap has reduced by one value and is only till 6. However, what if we kept the value that we deleted, 25, and inserted it at the last position? Now what is happening over here is, because we're always deleting the root element, which is always going to hold the maximum value, if we remove that and place it at the last index and then reheap our maximum heap structure, we're going to essentially, by deleting these elements, reach an array which is sorted. Let's go through it with an example. Alright, let's look at deletion in a max heap and see if we can sort our array by deleting the root element. Since in a max heap, we always only delete the root element. However, before we delete our root element, we take a temp variable and save the value of the root node. And then after that, we delete our root element. Now the root element is then taken over by the last element in the array, which is 6. Now 6 is compared with its children nodes, and whichever one's higher gets swapped with that position. 21 takes up the root node, and 6 gets swapped. Now we check if this node or this position still contains children nodes, which 2 into 4, 2 into I, which is 2 into 2, 4, there are still children node, so we compare, and whichever value is higher gets swapped into this position. Please note that this swap only happens if this value, which is swapped at the top, is lesser than the value at the children node to maintain the heap property. Now again, we check if this position contains children nodes, which 4 into 2, which is 2 into I, does not contain any children node, so we do not compare it, and we consider this heap a maximum heap. Let's try to understand if this is correct by doing what we are reordering our tree section. So we have 21 at our root node, we have 15 and 16 as its children, and 6 and 10 as 15's children, and 16's children is 4. At this point, this is a max heap, and we have a temp value, which is 4. We reduce the value of our heap height or heap index by 1, and this is now not the part of the heap. Therefore, we place the temp value or the root node outside the heap. After we've done that, let's continue with deleting our root elements till we reach till there are no elements to delete. So now we delete temp value 21, which is our root node, and swap it with 4. 4 gets moved and removed, and is then compared with its children. If the value is lesser than its children, the value in the children, which is higher, gets swapped, which is 16, so 16 gets swapped with 4. Now we check if 4 contains any children nodes, which 3 into 2, 6, there's no children nodes, so we do not compare any further. Now let's reorder our tree again and check if it's a max heap still. The root node value is now 16, its children is 15 and 4, and 15's children is 6 and 10. And this node doesn't exist. Now we have a value 21, which gets placed outside the heap. Now again, let's start by deleting our root node and saving its value first. We delete 16, we move 10 into its place, which is the last element in the array, and we remove 10 from here. Now, we compare it to its children. Since 15 is greater, we move 15 with the 10's position, and then we compare to 10's children, which is 6. 6 is lesser than 10, so no more swaps. At this point, let's reorder our tree again and see if we've satisfied our max heap property. We have the root node 15, which has children 10 and 4, and a node 6. At this point, let's delete our root node, which is 50, or before deleting that, we reduce our heap height and place 16 over here. Now, starting with deleting our root node again and saving its value, we move 6 into the first position and remove 6 from the array, and then compare it with its children. Since 10 is greater, 10 gets swapped, and 6 gets in the below position. Now at this point, because 6 doesn't have any children node, we leave it over there. And now let's reorder our tree and check if we still have a max heap. We have a root node 10 with children 6 and 4. This node gets deleted and our temp value gets loaded outside the heap, and heap reduces by 1. Now at this point, we delete our root node again, which has the value of 10. 4 gets moved into the root node. At this point, 4 is compared with its child, which is 6, and because 6 is greater, 4 and 6 are swapped. And now let's check if our tree is sorted or is still a max heap. We have a root node 6 with a child 4, and the temp value 10 gets loaded up outside the heap, and the heap value is reduced by 1. Now we delete our root node again, which is 6, and we move 4 into the root node. Now essentially, because nothing exists, we have 6 over here and 4. At this point, we can see by deleting the indexes or elements in the max heap and filling them outside the heap, we have sorted this array. And that's how heap sorting works. Now that we understand how heap sort works, let's try to implement it with a code. Alright, so let's look at our implementation of the heap sort, starting with our first function, max heapify. Max heapify function essentially makes sure that our heap property or max heap property is satisfied. The function takes the parameter, the array itself, the size of the array that it needs to satisfy heap properties over, and I, the index I, is going to be the index at which we are satisfying our heap properties over. And essentially we're doing I, and we're not putting a static link over there because we do not want to heapify the whole tree if we don't need to. And again, this is another case of divide and conquer. So first we set our largest element to the root index, or the root of the subtree that is being passed to us. We calculate the left child for the thing, for our root index, and as we saw from our visualization, the left child is at 2 into I. Now essentially in computers, because we start our arrays from 0, if we do 2 into 0, we're not going to have a root child, so we do 2 into I plus 1, and then our right child is going to be at 2 into I plus 2. Now once this is done, we're going to check if the left child and the right child are greater than the largest element, and if they are, we're going to swap the index of the largest. So essentially, before we do that, we check if left is within bounds. So if it's out of bounds, we never do this. And if left is within bounds, we check if our left is greater than the root element. Now, if this is the case, we swap our largest or our root index with whatever's at left. And if this is not the case, we check for right, and if right is greater, we swap right with the largest element over here. And essentially we don't put this inside a if else block, because we check if we, sorry, let me fix this. And we do not put this inside an if else statement because we need to check between right and left if the elements are greater than each other. So if left is greater than the right child, the left will remain at the largest. However, if right is greater than the left child, right is going to take the largest position. And this way we're avoiding doing one check in another line of code, thus optimizing our code. Now, if this is the case, now we need to check if our largest, the index at which the root was changed. So if largest is not equal to I, we need to do a couple things. if largest is not equal to I, we swap the our I with the index at which the largest element is present. So thus making our root node the largest element. Now, after we've done this, we need to recursively call our heap functionality over the subtree that we just swapped, and we do that by doing ARR, passing the array, the size of the array, and then we check the index, but we pass the index as largest because that is going to be the index that is going to be changed. Now this is our max heapify function. This is essentially, or was the most complex function in this functionality. The other thing that we need to do is this max heap function. The build max heap function is essentially going to build the max heap. Now we set the starting index of this max heap to n by 2 minus 1. Let me write this correctly. So essentially, we're doing this because this is setting the height to the last non-leaf node, because if we call the build max heap over a leaf node, the leaf node is always going to be satisfy the max heap property over itself, because it's going to be the largest element in itself. Therefore, we call it over the last non-leaf index. So essentially, if we have a tree that has 3 levels, we're going to call it over the second level at the non-leaf node. And after we've done this, we call a for loop. We start it at the starting index. We do it till we're not out of bounds, and we decrement our I because we are going from above to below, and we call our max heapify function. So the max heapify function again is going to make sure that our max heap properties are satisfied. So we pass that, and that is done for our building our max heap. Now coming to the heap sort function, and this is the function that is going to carry out the sorting functionality. And the first thing, as we see from the schematic of this function, is that we're following the same suit. We only pass in the array and the size of the array like we did with the other sorting functions. And the first thing that heap sort needs is to build a max heap. So we build a max heap over the array itself and over the size of the array. Those are the 2 parameters that build max heap needs. Now essentially, after that, as we saw, what needs to be done for heap sort? What we need to do is we need to take the first element, which is going to be the root element, and place it outside the heap. And after we've done that, we need to heapify it again. So that's what we're going to do inside this for loop. We're going to set our I to the size of the array, minus 1, because the array starts from 0. We are going to run it till our array is not out of bounds, and we are going to do I minus minus because we're starting from the right-hand side of the array. Now, after we've done this, inside, we are going to swap our root element, which is 0, with our last place, which is I, because we're starting at the right side. So we swap them. However, after we swap them, we saw that we needed to satisfy our heap properties. So we call our max heapify function over we call our max heapify function over the array that is affected. So we pass in the array itself, we pass in the index I, which is affected, and we pass in the index 0, And this is done because we're reducing the heap, so we're calling it over the reduced heap. And that essentially is how heap sort works. Hopefully this video was helpful to you, and I will see you for the next video. Thank you.